This lesson is on mass-mole particle conversions. So we're going to be converting from mass to moles. Sometimes we'll be converting from moles to mass. We'll also be converting from moles to representative particles or representative particles to moles. So let's review our representative particles because that depends on what type of substance that we have. So if we have an ionic compound, the representative particle is the formula unit. So this is for our ionic compounds, like sodium chloride or potassium nitrate. We have lowest whole number ratio of ions is what is meant by the formula unit. The molecule, this is when we have covalent compounds. Or the Hofbrinkel elements. So we have to remember those Hofbrinkels. So or, H, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. When we have these elements that are by themselves, not in a compound. When they're in the compound, they can have any subscript, but when they're by themselves, they have to have a subscript of 2. And then the atom then, of course, is for our other elements. Now, both the mole and the representative particles are counting units, which is different from mass. So our mass unit is grams and mole is moles. If we are going to be converting from grams of a substance to the counting number moles of a substance, we're going to use molar mass as a conversion factor. So we are going to use molar mass. If we're going from mass to moles or moles to mass. If we're going from the number of moles to the number of particles of a substance, then we're going to use Avogadro's number as a conversion factor. So here, our molar mass, we're going to have the grams in 1 mole. Here, for Avogadro's number, we're going to have 6.022 times 10 to the 23rd, and the particle could be a formula unit, a molecule, or an atom in 1 mole. So our conversion factors, remember, we can flip them if needed in the problem. So the moles and the particles, these are counting units, and then mass is a mass unit. Okay, so we're going to jump right into doing some problems, such as how many moles are in a 50.00 gram sample of lead, Roman numeral 2, nitrate. Okay, so we look at our problem and see what we have. We're given grams, we want moles, so that means we're going to use molar mass as a conversion factor. We learned how to calculate that yesterday. So our first order of business is to get the formula for lead 2 nitrate. Without that, we can't do anything. So we're going to use the rules. Lead is to the left of the staircase. It's a metal. We have Roman numerals. We use the stock system. So we write the symbol for lead Roman numeral 2, which is Pb with a 2 plus charge. Remember, the Roman numeral is the charge of the ion. Nitrate, ending in ate, it's a polyatomic ion. So that's NO3 minus. Cross your charges. Check your subscripts outside of the parentheses. 1 to 2 is a lowest whole number ratio. So our formula is Pb parentheses NO3 parentheses 2. Okay, now that we have that, now we're going to calculate the molar mass of that because we're going to need that to figure out our conversion. All right, so lead, we have one of those. Nitrogen, we have two of those. Oxygen, 2 times 3, we have 6 of those. And then remember, we go to our periodic table to get the masses of our elements. So lead, where's lead? There it is, 207.2. 207.2. Nitrogen, 14.01. And oxygen, 16.00. All right, and because this is 1 decimal place, 2 and 2, I'm just going to take this to 1 decimal place. Usually we do 2. All right, so let's add this up. 207.2 plus 2 times 14.01 plus 6 times 16 equals. All right, so I am getting a value of 331.2. And remember, this is the grams in 1 mole. So we could also say it's the atomic mass units in 1 formula unit. But here we need the grams and the moles. So now we're just going to do dimensional analysis. So we start out with our X. What are we looking for? We're looking for the moles. So X moles of PbNO32. Set that equal to our quantity of interest. We're interested in 50.00 grams of PbNO32. Put in our multiplication sign and crossbar. And now this is our conversion factor. So remember, we have grams in the numerator here. We need grams in the denominator so that it will cancel out. So we got to flip that conversion factor. So in the numerator, we have 1 mole of PbNO32 in 331.2 grams of PbNO32. So grams of lead, Roman numeral 2 nitrate cancel out. We have the units that we want, so that means we're finished with conversion factors. We put in our equal sign and we do our calculation. So 50 divided by 331.2 equals. All right, and we want to make sure that we do the correct number of significant figures. So 50.00 has 4 sig figs, 331.2 has 4 sig figs, so our answer must have 4 sig figs. So 0.1510 moles of PbNO32. So that's how I want you to do your answer. The number, the unit, and the formula. And I just want to say something. When you're doing this, when you have the same substance on both sides of the equal sign, you don't have to put the substance, but later on, we're going to have different substances on opposite sides of the equal sign, and then it's imperative that you put the substance formula. So I am going to put the substance formula. I think it's a good habit to get into, to always put what substance you are referring to after your unit. Okay, so let's do another problem. Okay, for this one, let's see, determine the number of grams in 2.75 moles of silver. Okay, so now we still have grams and moles. Grams and moles, you're always going to need a molar mass. So silver, our formula of silver is Ag. So we just get the molar mass right from the periodic table. We have 1 silver atom. So for silver, 107.87 grams are in 1 mole. Okay, so now let's do our dimensional analysis. So we're interested in the grams, so X grams of Ag equals 2.75 moles of Ag, multiplication sign and crossbar. So now we have moles here. We need to put moles in the denominator to be able to cancel out. So we use our conversion factor just like it is. So 107.87 grams of silver is in 1 mole of silver. Cancel out the moles of silver. And now we're going to do our math. 3 sig figs, 5 sig figs. We go with the smallest sig figs when we're multiplying and dividing. So our answer gets 3 sig figs. So 2.75 times 107.87 equals. Okay, so with 3 sig figs, we get 297 grams of silver. There's our answer. Number, unit, substance formula. Okay, let's see what our next one is. Let's see, how many molecules are in 235 grams of water? And that's about a cup. 235 grams is about a cup of water. So we want to know how many individual molecules are in that amount of water. Okay, when you have grams in the problem, you need to do your molar mass calculation. All right, so everyone knows the formula for water. That is H2O. So we have 2 hydrogens and 1 oxygen. On the periodic table, the value for hydrogen is 1.008, and our value for oxygen is 16.00. Let's add that up. So 2 times 1.008 plus 16 equals, and going to 2 decimal places, we get 18.02. And remember, that is the grams in 1 mole. It's also the atomic mass units in 1 molecule. Here we're going to use the grams in 1 mole because we have grams in our problem. Okay, let's do our dimensional analysis. So we're looking for the molecules. X molecules of water. Our quantity of interest is 235 grams of water. Multiplication sign and crossbar. So we're going to use this molar mass conversion factor because we need to cancel out these grams of water. And we're going to need to flip it because we have grams here. We need to have grams in the denominator. So 1 mole of water is 18.02 grams of water. So grams of water cancel out. Now, the units on the left is molecules of H2O. The unit on the right is moles of H2O. So that means we need another conversion factor because the units on the left have to match the units on the right. So how do we go from moles to molecules? Well, in a mole, we have the Avogadro's number conversion factor. So there are 6.022 times 10 to the 23rd molecules of water in 1 mole of water. So 6.022 times 10 to the 23rd molecules of water are in 1 mole of water. So moles of water cancels out. So the only unit that has not been canceled out on the right is molecules of H2O, which matches what we're looking for. So there's our unit, molecules of H2O. Now we do the math. 3 sig figs, 4 sig figs, 4 sig figs. So 3 sig figs for our answer. So 235 divided by 18.02 times 6.022 times 10 to the 23rd equals. Okay, we're going to get a really huge number, so don't forget your exponent. So with 3 sig figs, we get 7.85 times 10 to the 24th molecules of H2O. Number, unit, formula. Alrighty, what are we going to do next? Next, what is the mass of 0.43 moles of a sample of solid iodine? Okay, so we have the element iodine. When we have elements, we have to check, is this a Hofbrinkel? So remember our Hofbrinkels, HOFBRINCL. Iodine, here it is. It is a Hofbrinkel. That means the formula for our sample of iodine is I2. So now we have to do our molar mass. We have 2 iodine atoms. So look on the periodic table for iodine, and we have 126.90. And we have to multiply that by 2. 126.9 times 2. And we get 253.80. That's grams of I2 in 1 mole of I2. So we care about Hofbrinkels, or we worry about them, when we have those elements by themselves. If iodine was in a compound, its subscript would depend on the compound, but by itself, we have to have I2. So now we can go ahead and do our dimensional analysis. So X grams, we're looking for mass of I2. Set that equal to our quantity of interest, 0.43 moles of I2. Multiplication sign in crossbar. So this is our conversion factor to use. So 1 mole goes in the denominator so that we can cross it out. And 253.80 grams of I2 goes in the numerator. Moles of I2 cancels out. 2 sig figs, 5 sig figs. Our answer needs 2 sig figs. 0.43 times 253.8 equals, let's see, with 2 sig figs, that would be 110 grams of I2. Number, unit, formula. Okay, we're going to do one more. Let's see, how many formula units? How many formula units of iron, Roman numeral 3, hydroxide, are in 1.62 moles of the compound? All right, so let's get our formula for iron, Roman numeral 3, hydroxide. All right, so this is when we're using the stock system. So iron, Fe, Roman numeral 3 means 3 plus. Hydroxide, polyatomic ion, check your chart. And it is OH with a -1 charge. Cross, 1 and 3 is low number hole ratio. So we get Fe parentheses, OH parentheses 3. Now we check our problem. Do we need to do a molar mass calculation? We're looking for formula units. This is a counting unit. We're given moles. That's a counting unit. If we go back to our chart that we made at the beginning, moles and particles, formula units and moles, we're just using Avogadro's number. We don't need the molar mass. You can calculate it, but you're not going to use it. The only conversion we need is Avogadro's number. Okay, so X, formula units of FeOH3 are equal to our quantity of interest, 1.62 moles of Fe parentheses OH parentheses 3 times. So in Avogadro's number, it's always, we always have 6.022 times 10 to the 23rd. This time we have formula units in 1 mole of FeOH3. And have room to write the formula there. So moles cancel out. So our unit is formula units. Formula units of FeOH3. 3 sig figs, 4 sig figs. So 3 sig figs, 1.62 times 6.022 times 10 to the 23rd equals, so we get 9.76 times 10 to the 23rd formula units of FeOH3. So when you're doing these problems today, go back to this for what conversion factors you need. If it's mass to mole or moles to mass, you only need one conversion factor, the molar mass. Moles to particles, particles to moles, one conversion factor, Avogadro's number. But if you're going from mass to particles or particles to mass, then you're going to need both of these conversion factor. And which one you use depends on the problem. Just make sure you're canceling units every time you write in a conversion factor. All right, that's it.